It begins not with a bang, but with a whisper that echoed across control rooms, laboratories, and coffee-stained notebooks. For 12 years, astronomers, engineers, and cosmologists waited with a kind of quiet reverence, anticipating something extraordinary, something that could illuminate the darkness that has haunted cosmology for decades. And now the silence has been broken. The images are here. Not just any pictures, not just snapshots of stars or galaxies. These are the telescope images scientists have been waiting 12 years for. The kind that rewire how we see everything, from the smallest celestial dance to the vast scaffolding of the universe itself. These aren't just pictures, they're cosmic revelations. In July 2023, the European Space Agency launched the Euclid Space Telescope from Cape Canaveral, Florida. A moment that seemed quiet to most of the world, but to those who had dedicated over a decade of their lives to this mission, it was the culmination of sleepless nights, agonizing design revisions, failed simulations, and relentless optimism. Euclid wasn't built to simply take beautiful pictures. It was engineered with a purpose so ambitious, so sweeping, that even those closest to the project were hesitant to promise its full potential. Its mission? To chart the dark universe. Not just to map galaxies and stars, but to map what lies between them, the hidden architecture of the cosmos, shaped by something we cannot see but whose fingerprints are everywhere: dark matter and dark energy. The anticipation has been building since Euclid's concept phase in 2011. Over the years, science marched forward. NASA's James Webb Space Telescope dazzled the world with its infrared snapshots of distant worlds and nebulae. Gaia continued its meticulous star census from Earth's orbit, and countless ground-based surveys scanned the skies with increasing fidelity. But none of them could do what Euclid was born to do: to simultaneously capture an ultra-wide field of view with unprecedented resolution across both visible and near-infrared wavelengths. It was a gap that no existing observatory could fill, a blind spot in our cosmic vision that Euclid was built to correct. Once launched, Euclid didn't simply hang above our heads. It was sent to orbit the second Sun-Earth Lagrange point, known as L2, a gravitational balancing point some 1.5 million kilometers from Earth. It now shares that orbital space with giants like the James Webb Space Telescope and Gaia, a neighborhood of tools that are changing astronomy as we know it. From this vantage point, Euclid is free of Earth's atmosphere, unburdened by the distortions of weather or light pollution. The sun, moon, and Earth always stay behind it, giving Euclid a crystal-clear view of the cosmos and uninterrupted communication with mission control. By October 2024, data from Euclid began to trickle back. The raw images arrived, followed by the long processing hours needed to transform them into something meaningful. Each pixel telling a story of distance, of light, of time itself. Scientists gathered around screens as the first complete mosaics took shape, each revealing slices of sky spanning hundreds of millions of light years, stitched from hundreds of smaller frames. They were unlike anything anyone had seen before. They weren't just pretty, they were profound. Every image contained millions of galaxies, each an island of stars, gas, and dust, many dating back over 10 billion years. And in between, the gravitational fingerprints of dark matter bent and warped the very light we saw, like ripples on a pond distorting the reflection of the moon. This process, gravitational lensing, is one of Euclid's key strengths. It doesn't need to see dark matter directly. It reads its presence by observing the way galaxies are subtly stretched and curved by invisible mass. And it does this across the sky, in a wide enough sweep to uncover the grand patterns of cosmic structure, the threads, the filaments, the knots of galaxy clusters, where matter has clumped together under gravity over billions of years. Euclid is giving us not just a static map, but a dynamic one. It charts how structure evolved, how galaxies were drawn together, and most importantly, what unseen forces, dark matter and dark energy, have shaped their paths. Among the first images released was a mosaic constructed from 260 overlapping frames, taken between March the 25th and April 8th, 2024. It covers a region of the sky 500 times larger than the full moon. And yet, astonishingly, this accounts for just 1% of Euclid's planned survey. Even in this small sliver, the depth is staggering. Not only does it allow astronomers to zoom in from large-scale structure down to individual galaxies, but it also captures stars within those galaxies, and even hints of the interstellar clouds that cradle star formation. It's as if someone finally handed us the glasses we needed to see the universe in high definition. And the effect is, quite literally, breathtaking. Consider the image of the Perseus cluster, one of the most massive known galaxy clusters, located some 240 million light-years away. In a single frame, Euclid revealed over 1,000 galaxies belonging to the cluster and more than 100,000 galaxies further in the background. But it wasn't just the numbers that stunned scientists. It was the organization. The galaxies weren't scattered at random. They formed filaments and arcs, hinting at gravitational patterns guided by vast quantities of dark matter. Without dark matter, the distribution would be much more uniform. But that's not what Euclid showed. Instead, it confirmed the large-scale clumping that theorists have long predicted but struggled to visualize. Perhaps more surprisingly, Euclid detected over 630 dwarf galaxies within the Perseus cluster, tiny, faint objects missed by previous surveys. These galaxies are particularly interesting because they are thought to contain very high proportions of dark matter. Studying them can reveal not just how dark matter behaves on large scales, but also how it may influence star formation and galactic dynamics on small ones. Another breathtaking image focused on the irregular galaxy NG C6822, just 1.6 million light-years away. Discovered a century ago by Edwin Hubble, this galaxy had been observed before by JWST, but only in narrow focus glimpses. Euclid, with its wide-angle view, placed the entire galaxy into context, showing not just its stars and clusters, but its environment, the surrounding regions of space that influence its shape and motion. Scientists immediately noted the clarity with which globular clusters and HII regions appeared. Those glowing gas clouds where new stars are born. More than just pretty, these features provide crucial clues to the chemical composition and evolutionary history of galaxies. In NGC 6822, the stars are low in metals, suggesting they formed in a universe that hadn't yet been enriched by supernovae. That makes this galaxy a kind of living fossil, a record of star formation in a younger, simpler cosmos. Each of these images is a testament to what patient, focused science can achieve. They are more than just milestones. They are mirrors held up to the universe, revealing not only where we are, but how we got here. And just when it felt like Euclid had already delivered the most powerful images the scientific community had seen in a generation, the telescope turned its gaze closer to home, relatively speaking. The next target wasn't a distant cluster or a mysterious filament in deep space, but something right in our galactic neighborhood, the globular cluster NGC 6397. Located just 7,800 light-years from Earth, it's the second closest globular cluster to our planet. Globular clusters are dense, spherical collections of tens of thousands, sometimes even millions, of stars, bound tightly by gravity and often older than the galaxies they orbit. To astronomers, they are cosmic time capsules. Previous images of NGC 6397 from telescopes like Hubble offered detailed views of its bright central region, but they always came at a cost, a limited field of view. Euclid changed that in just 1 hour. Its powerful optics and wide-angle capabilities captured both the blazing core and the faint, whispering stars trailing off in the outskirts. These faint stars, often too dim to resolve in older images, are essential. They're clues to the Milky Way's own history, how it formed, what materials were available in the early universe, and how star formation unfolded in environments where heavy elements were rare. Some of the stars in NGC 6397 are over 13 billion years old. They existed when the universe was a fraction of its current age, long before the Earth formed, long before our sun ignited. Studying such a cluster isn't just about understanding stars. It's about reconstructing the early conditions of the universe. And Euclid's ability to observe faint outer stars, previously lost to the darkness, means astronomers now have access to critical population data they've never had before. These stars hold the potential to tell us whether globular clusters were born in isolation or were the remnants of ancient, cannibalized galaxies absorbed by larger ones like the Milky Way. Every pinpoint of light has a story. Now, we can finally read those stories at scale. But the surprises weren't limited to clusters or irregular galaxies. One of the most astonishing demonstrations of Euclid's capabilities came when it captured Caldwell 5, an entire spiral galaxy hidden behind the dense, dusty plain of the Milky Way. Located about 11 million light-years away, Caldwell 5 had always been difficult to study, not because it's inherently faint or far away, but because of its unfortunate position. It lies directly behind our galaxy's thickest curtain of dust. For most telescopes, especially those reliant on visible light, this region is impenetrable. But Euclid, with its near-infrared imaging system, sees right through that obscuring haze. And what it revealed was stunning. The image wasn't just a dusty smear punctuated by a few dim stars. Euclid revealed the full sweeping arms of Caldwell 5, tracing the spiral structure with precision. You could see individual stars, star-forming regions, and massive clusters of young, hot suns glowing in the infrared. The resemblance to our own Milky Way was immediately striking. Studying Caldwell 5 gives us a mirror, an external perspective on what our own galaxy might look like to an observer millions of light-years away. This is critical because we can never truly step outside the Milky Way to see it whole. Caldwell 5 offers that rare chance, a structural and evolutionary analog that we can observe in full, finally uncloaked. Even more importantly, because Euclid can peer through the galactic dust, it means we now have access to an entire region of sky that was once essentially invisible. For decades, astronomers referred to it as the zone of avoidance, a portion of the celestial sphere blocked by our galaxy's own emissions. Now, thanks to Euclid, that zone has become fertile ground for discovery. We're no longer blind to what's hiding behind our own cosmic backyard. And then came the image that perhaps best symbolized Euclid's power, the Horsehead Nebula. A favorite among amateur astronomers and a fixture in textbooks, the Horsehead sits about 1,375 light-years away, near the iconic belt of the Orion constellation. It's a massive star-forming region, a cold, dense cloud of hydrogen gas silhouetted against a brighter background of ionized gas. Other telescopes have imaged it before, most famously Hubble and more recently JWST. But none had done what Euclid did, captured it in its entirety, in full sharpness and with context. This was the widest and sharpest image of the Horsehead Nebula ever taken. It revealed not just the striking silhouette of the nebula itself, but the surrounding field of stars, the faint filaments of gas, and, crucially, countless potential free-floating planets. These are planets that roam the galaxy not bound to any star. Invisible to most surveys, they can be detected through their faint glow in infrared and through gravitational microlensing, both of which fall within Euclid's observational toolkit. In this image alone, astronomers believe they've found evidence of many Jupiter-mass planets wandering through space untethered, relics of disrupted planetary systems or perhaps objects that never formed around a star to begin with. One such object identified in the broader Orion complex is S Ori 62, a massive rogue planet over 10 times the mass of Jupiter, with an estimated temperature of 1,200 degrees Celsius. It's not a lone anomaly. It's likely one of hundreds, maybe thousands, of such planets waiting to be cataloged. Euclid's data is revealing that free-floating planets might be far more common than we previously thought. If confirmed, this discovery alone would reshape our understanding of how planets form and what kinds of environments they can exist in. But even as the headlines celebrate the beauty and novelty of these images, there's something deeper happening, something profoundly unsettling, and at the same time, exhilarating. With every new frame, Euclid isn't just painting a prettier picture of the universe. It's poking holes in long-held assumptions. The distribution of matter, the growth of galactic structures, the behavior of dwarf galaxies, the abundance of rogue planets. Each of these revelations is a test, and in many cases, a challenge to our existing models of cosmology. For instance, dark matter, The mysterious substance that doesn't emit, absorb, or reflect light has always been inferred from its gravitational effects. Euclid's gravitational lensing maps provide a direct view of where this dark matter is, not just that it exists. And the early returns suggest some discrepancies between what the models predict and what we're seeing. If these anomalies persist, we may be facing a need to revise some of the foundational pillars of physics, much as Einstein's theories once upended Newtonian mechanics. That's part of what makes Euclid so vital. It's not just confirming what we think we know, it's questioning it. And that's the sign of great science. The telescope was designed not to provide comfortable answers, but to generate the kind of uncomfortable data that demands deeper investigation. Its wide field of view, high resolution, and dual capability in both visible and infrared make it uniquely suited to explore everything from the age of reionization to the current acceleration of cosmic expansion. Still, for all its technical power and scientific ambition, Euclid's images carry something more emotional. There's a stillness to them, a haunting, beautiful silence that stretches across billions of light years. When you look at these pictures, the Perseus Cluster, the Horsehead Nebula, Caldwell 5, you're not just seeing space, you're seeing time. Light that left its source before there were humans on Earth, before the Earth even existed. And now that ancient light is ending its journey in the sensors of a telescope that took 12 years to build, operated by people who may never live to see the full scope of its legacy. It is humbling, it is awe-inspiring, and it is only just beginning. As Euclid's mission pushes forward, the weight of what it's capable of starts to truly settle in, not just on the shoulders of scientists, but on anyone who dares to look up and try to comprehend what they're seeing. Because this isn't just a telescope pointed at the sky. It's a time machine, a cartographer, and a silent provocateur all at once. For more than a decade, scientists waited for this moment, waited through delays, funding negotiations, engineering setbacks, international collaborations, and relentless testing. 12 years to get here, to Lagrange Point 2, where Euclid now orbits in silent coordination with Gaia and the James Webb Space Telescope. And finally, it has begun delivering the very images and data that were once only theories, renderings, simulations. Now they're real, and the scientific community is scrambling to catch up with the magnitude of what's been released. Only 1% of Euclid's full sky survey has been captured so far. Just 1%. Yet in that single sliver, we've already cataloged more than 100,000 galaxies behind known clusters. We've found new dwarf galaxies never seen before. We've resolved faint stars in dense regions that were previously unreachable. Every image, every pixel, is a layer peeled back from the cosmic onion, exposing new structures, new forces, and most provocatively, new questions. Because that's the paradox of space science. The better our tools become, the more we discover how little we actually know. Take, for instance, the evolving discussion around the distribution of dark matter. With Euclid's ultra-precise gravitational lensing maps, scientists can now trace how massive structures bend the light of background galaxies, revealing where dark matter must exist based on distortions. But early data has already raised eyebrows. The patterns of distortion, the density of clumps, the filamentary structures connecting galaxy clusters, some of it doesn't entirely align with the predictions made by our standard cosmological models. It's not enough yet to declare a scientific crisis, but it's more than enough to get theorists back to their chalkboards. If Euclid continues to detect inconsistencies in the way dark matter structures appear versus how we believe they should form, it might indicate that our current understanding of dark matter, or gravity itself, is incomplete. That's the kind of quiet revolution Euclid is triggering. Not with bombast or dramatics, but with evidence, with clarity, with sheer observational power. It doesn't shout, it simply shows. And what it's showing is that the universe is far more complex, far more layered than we've allowed ourselves to believe. It's reminding us that when we stare into the dark might just stare back, with structure, with depth, and with secrets yet to be unfolded. But what makes Euclid so deeply different from other missions isn't just its power to image. It's its ability to map time itself. Because of its spectroscopic capabilities, particularly through the near-infrared spectrometer and photometer, or NISP, it doesn't just take pictures. It measures redshifts. It calculates how fast galaxies are moving away from us, how far back in time their light was emitted. This allows Euclid to place each object it sees into a 3D context, not just where it is, but when it is. And this changes everything. For the first time in human history, we're constructing a three-dimensional map of the dark matter scaffold that underpins the universe. Not just a static model, but an evolving one. It's like watching a web form over billions of years, tracing how galaxies were drawn together, how clusters formed, how voids expanded. This isn't just a pretty diagram or a set of coordinates. It's a living timeline of existence, stitched together from light that has traveled unimaginable distances just to be registered in Euclid sensors. And perhaps most poignantly, all of this is only possible because of collaboration. Euclid is a European Space Agency mission, yes, but it stands on the shoulders of international cooperation. NASA provided critical components. Engineers and scientists from across Europe, the United States and beyond worked tirelessly for over a decade to make this dream real. It's a rare moment in history when political borders are erased in favor of something greater, something cosmological, something human. We often look at space as the final frontier, as the place we might one day go. But Euclid isn't about going, it's about seeing, and through that seeing, understanding. The telescope is not for tourists, it's not for thrill seekers or colonists, it's for the questioners, for the ones who ask what came before, what lies beneath, and how the story was written long before we had words to tell it. It's for the dreamers who know that reality is stranger than fiction, and that the best way to grasp the truth of existence is not to invent it, but to observe it. And it's only just begun. Euclid's primary mission is scheduled to run for 6 years. That's 6 years of continuous imaging, mapping, scanning, and uncovering. Each year the map grows. Each observation adds to the cumulative understanding of our place in the cosmic web. We'll see galaxies at the moment of their birth, observe stars in the final gasps of their lives, and detect gravitational distortions from invisible forces that shape everything we see. As we progress, there will be more surprises, more contradictions, more beauty. Euclid may discover structures we didn't know existed, galaxies with anomalous properties, stars older than our current models allow. It may even detect signs of exotic physics, variations in dark energy density, fluctuations in fundamental constants, perhaps even clues pointing to a fifth force beyond the known four. If so, it won't do so with fireworks. It will do so with quiet, steady observation, frame after frame, year after year. That's the beauty of a mission like this. It's not loud, it's patient. It waits, it watches, and it gives us the privilege of seeing what has always been there, but just beyond reach. In a time when most headlines are loud, frantic, and temporary, Euclid offers something else entirely: permanence, wonder, a kind of perspective that few things in life can provide. It reminds us that the universe is vast, not just in size, but in depth, that looking outward is, in a strange way, also looking inward, at what it means to be alive, to question, to yearn for knowledge. So when scientists say they've been waiting 12 years for these images, it's not just about the time spent building the telescope, it's about the centuries of longing behind it, the ancient human urge to understand the stars, the sleepless nights spent coding, calibrating, testing, the generations of astronomers who built the theories, who argued and debated in papers, in classrooms and observatories. All of that waiting, all of that effort led to this moment. And now, with Euclid's eyes wide open, the wait is over. The universe is revealing itself, not in a single blinding revelation, but in countless stunning frames. It is vast, it is ancient, it is elegant beyond comprehension. And for the first time, we can see it with the clarity we've only dreamed of. This is the beginning of a new map, not a flat one, not a static one, but a living, breathing map of space and time. And for those willing to follow it, the journey has only just begun.